So our first speaker is Taekyun Kim. Taekyun is a postdoctoral fellow at the Kellogg School of Management and at NICO, where he works with Professor Haejin Yoon. Taekyun's research focuses on how emerging technologies such as AI and robotics affect strategic decisions and economic outcomes. Recently, his research interest has focused on computational social science, and today he is going to discuss how legal systems are becoming less disruptive over time.
Thank you. So thank you for the great introduction. So my name is Taekyun. I'm a postdoc fellow at Kellogg School of Management, and this is one paper that we are working with Haejin and Jisung, and this is about the legal system and its evolution in the US context. So recently we have observed an exponential growth of both science and technology, and we have developed and deployed these new innovations, and we used these new innovations into our daily life and operations, business operations as well. So from the use of these new technologies, we have generated a lot of great enhancement of productivity gains, which in turn economic growth as well. However, on the other side of these new innovations, there has been always dark side of new technologies. So this is one example of recently observed within the use of artificial intelligence. So there was an issue of deepfake of Taylor Swift, and it was produced as a pornographic, and it is distributed across the X and Meta and Facebook as well. So these platform firms try to regulate these deepfake with the AI tagging project something, and the legal systems also try to regulate by establishing new legislations. So for the use of better and responsible use of these new innovations, there emerges the role of legal system as well. So legal system gets really important, and the legal system also keep up with new science and technology and the changes and new paradigms driven by these new technologies. Despite this importance, there is limited understanding about the legal system, but there are a bunch of studies that examines about the science and technologies. This is one paper from Nature, and they measure disruptiveness of science and technology based on these citation measures. So these results basically suggest that scientific and technological disruptions are becoming more difficult, which means producing high impact science and technology is really difficult as well. Then what about the case of the legal system that should follow and keep up with the science and technology? That is our research questions. So we examine how is law evolving over time, and to examine that issue, we use citation network, and we examine the stability and dependency of legal systems. So to do that, there are a bunch of variety of laws within the US, including code of states or constitutions or data case laws. But in this paper, we particularly focus on this case law data in the US. So the data includes around 6 million case laws in the US, and the time window is around 1600 to 2020. And the data include decision information and court information, and most importantly, citation information, which is like this. We are going to use the exactly same measure for disruptions and how the evolution of legal system is changing over time. So as we show this graph of number of laws here, let's get back to here and get back to the network again. So this graph shows that the x-axis is about the number of population, and y-axis is about the number of case laws. So there is beta equals 1, there is gray area. So with the growth of population, there is much more generation of case laws, which means as population increases, there arises more need for the number of case laws. So as what it means is that as society gets more complex, this complex society requires much more regulations and coordinations for these increased populations. And this is one graph that we extracted from the case law network. So as you can see, each color represents its community. So as probably expected, this legal system also has some kind of their own community with specific classifications, as similar with the other scientific findings. So it's within this legal system, it's not really random. It has some kind of systematic within this network as well. Then can we use that disruption measures within the legal system? Can we apply that measure to our context? So to illustrate that, we provide several examples to illustrate that issue. The first one is about the Brown and Board of Education. So before this law, there was a rule based on this Plessy and Ferguson, which argued that there should be separate public schools for white and Black people. And this law lasted around 60 years. And with this Brown and Board of Education, it overruled the previous rule, and people for both white and Black people were able to go to the same public schools. So it looks like very disruptive and important. And from the network perspective, it is also true. So it gets more citations directly from the future case laws than the other case of the vocal and backward citations only. So it has a value of around 0.22 here. And the other case of the Plessy and Ferguson, which instead of the separation for white and Black people, it gets almost zero. So it became obsolete by this Brown and Board of Educations. And the other example is Marbury and Madison. It sounds a little bit difficult, but let's get back to the previous example. The decision was made based on this Constitution. So this kind of behavior is set up by this case law. So every decision at the end should be based on Constitution. So it sounds so fundamental, and if we look at the network perspective, it has maximum value of 1. So it is based on the Constitution, and this rule is followed by majority of countries. So so our measurement for disruption or the legal system is a little bit working on our context as well. So based on that validation, we try to identify some distribution of disruptions in the legal system. Interestingly, in the legal system, there are a lot of highly disruptive cases, which is a little bit different from, for example, with the academic papers. So in case of academic paper, there are some highly disruptive cases for Nobel Prize papers. For the consolidating paper, there are some papers like review articles, which is a little bit evenly distributed, but for the legal system, it is highly distributed to large-scale way. And so this is a key finding of our paper. So similar with the paper, academic paper and technological advances, we also observe the same pattern of declining of disruptions over time. It is because probably, as I mentioned before, foundational laws such as related with human rights and something fundamental have already established in the past, and to generate or to make something very important for this case law is almost difficult, as shown in the same case with paper and technologies as well. So within this disruption of laws, we try to identify a potential mechanism of these laws. So then where does this disruptive laws come from? That was our question. So we tried to, among variety of explanation, we particularly focus on this political ideology. So we recently see some examples of movements for human rights and environmental protests, which frequently happened in more liberal states. For example, we recently have seen the movement of Black Lives Matter, which was held in Minneapolis, where the governors are predominantly a Democratic Party for almost 30 years. So it seems like there must be some kind of correlation between political ideology of states and disruption of laws. So then we try to investigate the relationship between liberal ideology and law disruptions. We use the data of state ideology by Perry et al. So the dependent variable was this disruption of laws, and independent variable is state political ideology, which as the higher value indicates more liberal political ideologies. And we control also the number of laws in a given year. And we also included fixed effects for code types and reasons as well. So the results shows that there is a positive relationship, which is a little bit weak, but it has shown some kind of correlation between state political ideology and law disruptions. And then what about some different perspective that is different from technological advance and scientific discoveries? And I would say legal system has hierarchy, so which gives more power to certain courts. And these courts has more power to overrule the previous laws, which is a little bit different from technological and scientific domains, because they have some kind of prestigious journals like Science and Nature. It is prestigious, but it doesn't have any power, like the designed power similar with the like this. So majority of disruptions are normally arise from Supreme Courts with higher level of priority. So this is key takeaway for this talk. So there is scientific and technological advances. And from that, we see a lot of new products and services are developed. But to harmonize with that issue, the legal system also plays a crucial role in establishing regulations and governance to ensure more responsible and ethical and efficient use of these advances. So let me finish my presentation with the emphasis of the co-evolution of scientific and technological advances and legal systems. It's almost 15 minutes. Thank you so much.
We have a few minutes for questions before we go to our next speaker.
I'm not sure if I missed this detail, but when you're analyzing the disruptiveness of the legal system over time, are you specifically looking at cases related to regulating scientific contributions, or are you just looking at legal cases in general?
In general.
Oh, okay. So then what's the relationship between scientific advances and legal cases?
It's not directly, but it has similar pattern. So we probably will go deeper into the connection between science and technology as well.
Okay, cool.
So, I'm having a little trouble of seeing the analogy, right? Why? Because in the legal system, you can think that there are sort of opposing forces that are trying to change the law in different directions, right? Mm-hmm. So you would have the racists that want to keep the races separate. You would have, the misogynists that want to keep women having no rights. And so you could see the history of the legal system as a struggle between these groups with different positions. And if I think about the legal system in that way, then I think that an analogy to earthquakes is sort of a better analogy than one in which you are kind of evolving towards building new knowledge. And what I mean is that you could say, like, Plessy came in and sort of it set up a situation in which you no longer could have slaves, but you could have segregation, right? And said segregation is constitutional. And that was a status quo for a long time. But just like in an earthquake, what gives rise to an earthquake is that there is tension building, right? And then Brown versus Board of Education was sort of kind of a release. And you could imagine that whenever these releases occur, there is a big catastrophic change in a sense. And then there are sort of lots of aftershocks afterward, which be consistent with some kind of thing in which you have a decrease over time because of this stability. And so I think the way to separate the two possibilities would be if you had much longer data, right? So I think that it would be important for you to provide a more mechanistic justification of why the comparison to science is a good one, right? Because I think about science and the legal process as having very different characteristics. And so the interpretation of the data would depend on that.
Okay.
Sorry, there was no question.
Oh, but it's great comments. Yeah, thank you.
Question over here.
So I have a question about a confounding variable in disruptiveness is we see disruptiveness go down over time as the citation network becomes ever more interconnected and dense. And I wonder how you control for that, because that seems to be happening in the legal system as well, where people have better tools to become aware of case precedents and communicate with other lawyers to know which cases they need to cite, which arguments are likely to be successful. So is there a way to control for how densely connected the network is becoming with this disruption measure?
At the moment, I'm not sure, and probably our team will try to figure out the way to control for it. Yep, thank you.
Just a quick comment. I think it kind of builds on what Luis is saying. One thing about law is if you're going to create disruption based relative to something in the past, then you miss all the things in law that are original, that don't relate to laws in the past that actually were very disruptive by creating a law where none existed prior to it. So I would say in thinking about this, one way to kind of integrate some of the things that Luis has been mentioning is to think about disruption in this context with that in mind.
Right.
Okay, thank you. We will now move to our second speaker. Feihong Xu is a PhD candidate with the Interdisciplinary Biology Sciences Graduate Program, and she also works with Luis Amaral at the Amaral Lab. Her research focuses on data-driven machine learning methods for temporal disease subphenotyping and prognosis based on electronic records and datasets. Today, she's going to discuss the robust extraction of pneumonia-associated clinical states from electronic health records. Just as soon as we get the microphone on. All right, take it away.
Thank you, Andy. Hi everyone, I'm Feihong, a graduate student from the Amaral Lab. Today I'll share with you our research on the robust extraction of pneumonia-associated clinical states from electronic health records. Pneumonia, the inflammation of the lung, is the leading cause of mortality worldwide. Around 20% of pneumonia patients require at least one admission to ICU. It is also the most common secondary complication within the ICU. Pneumonia is not a standalone, well-dedicated disease, but rather heterogeneous. It can be caused by various pathogens, including bacteria, virus, and in rare cases, fungi. It can be acquired through community, within hospital, or associated with mechanical ventilation. Its progression is also affected by various risk factors such as sepsis or ARDS. We're interested in learning pneumonia progression black box through which patients either recover or deteriorate. We hypothesize that there may be different clinical states and patients may move in different ways among them. The Script Consortium collected electronic health records for 600 patients with severe pneumonia. These patients were mechanically ventilated, admitted to ICU, and undergone bronchoalveolar lavage, which is a diagnosis tool for pneumonia. In total, these patients spent more than 13,000 days in ICU, which is the focus of this study. Electronic health records provide a unique opportunity in studying clinical states and disease progression. It contains very rich information of large population of patients across long periods of time, including their demographics, vital signs, laboratory tests, clinical notes, and severity scores. However, electronic health records are observational in nature and is not collected for the purpose of research particularly. Thus, there are data-related challenges. Our data is irregular time series in nature. Here shown as an example, the body temperature colored blue here and lactate concentration colored red here of a patient through the ICU stay. We can see that the scale of two clinical features are vastly different, and they are recorded irregularly at different sampling frequencies. We regularize such time series by a per-day window. And for features that's recorded multiple times per day, we aggregate it by descriptive statistics like mean, median, standard deviation, etc. And of course, there are features that's less frequently recorded and sets are missing for certain days. And as we include less and less frequently recorded features, our data becomes sparse and sparse not at random. To properly pre-process such heterogeneous, high-dimensional, irregular, and sparse not at random data, we need a ground truth to benchmark our pre-processing strategies upon. Despite that we don't know the ground truth of clinical states within the black box, we know that upon discharge, patients who fully recover and patients who unfortunately die are in objectively vastly different states. And we benchmark and optimize our pre-processing strategies towards better separation of these two extreme clinical states. Here as an example, we decided to use carry last forward with a limit of imputation gap 1 as our imputation method because this method achieves the highest separation between these two extreme clinical states measured by a silhouette coefficient here. Similarly, we made other choices. We use min-max normalization. We selected 15 the most frequently recorded clinical features. And after data imputation, we are left with more than 8,000 patient days. We choose the top 4 principal components. And indeed, the two extreme states separate pretty well in our curated PCA space. And using a Gaussian mixed model, the discriminant accuracy is higher than 95%. Now we're ready to identify the clinical states, i.e. clusters in the PCA space. However, traditional ways of clustering fail to identify robust, reproducible, or consensus clusters. Here I'm showing as an example the spurious clusters indicated by orange circles here, whose centers do not even fall within the regions with high density. That's identified by Gaussian mixed model. We also examined the consistency of clustering solutions from different clustering algorithms of the same data set. And this consistency is measured by adjusted rand index. We can see that different clustering algorithms don't agree with each other. We also examined the consistency of the same clustering algorithm on bootstrapped data points, and we can see they don't even agree with themselves. Long story short, we improved the robustness of density peak clustering by ensemble and bootstrapping methods. I'm happy to talk more about these methods later, but here I'm showing a demonstration of improved consistency across bootstrapped samples measured by adjusted rand index, again, of our ensemble density peak clustering compared with original density peak clustering. And this benchmark is done upon synthetic noisy dataset. This is the two-dimensional data, and the gray points here represents uniform noise background, and color dots represent clusters generated by Gaussian distribution. Using our ensemble density peak clustering, we can see here 4 clusters can be readily identified from our data. And this is what it looks like in the curated PCA space. We can look at how the endpoints of patient days fall within these 4 states. We can see that the capital D states contains almost exclusively patient days close to expiration. On the contrary, the capital S states includes mostly patients who fully recover, represented as blue bars here. We later also established association of the V states with viral infection and NV states with non-viral infection. In summary, utilizing robust preprocessing pipeline and robust and ensemble density peak clustering methods, we were able to identify 4 robust clinical states from ICU patients with pneumonia. 2 of the states are associated with final disposition. The other 2 states are associated with etiology, i.e. virus versus non-viral infection. We also know that our clustering methods is not exhaustive, which means there may probably be other states that's not captured due to either data or algorithm limitation. We later also find that patients experience more and more favorable transitions to favorable states during their recovery. I want to thank Amara Lab for all the support and help, and this work is done while I was supported by the biotechnology training program. This data is collected, organized, and distributed by the Script Consortium. I would like to especially thank Thomas Stoker and Kathy Gall for their helpful discussion. And thank you for listening.
For questions? Grab it from the
Hi, I have a question. So if you pick your data preprocessing approach based on how well it clusters things into like alive versus dead, doesn't that kind of bias your later results to also be clustered into whether or not they're alive or dead?
Yes, I think this pre-processing pipeline would especially favor the separation of mortality versus, say, for example, the separation of etiology or say the type of acquisition, like whether it's acquired from community or hospital, etc. But I don't view this bias as a disadvantage, because we are indeed more interested in the stratification of patients based on the severity of their disease. And second, since we also find a strong association of our two states with etiology, so viral infection versus non-viral infection, this demonstrates that it also manifests variation at other dimension besides mortality.
Okay, thank you.
Thanks.
So I wonder how generalizable the model is to other demographics, and whether you did any study for to test the performance of the model to out of sample data coming from other external data centers or something like that.
Yeah, that's a great question. I think it would be very helpful to test this pipeline and our especially the clustering methods in patient data from other medical centers. But I haven't got data from other hospitals. And also, I would expect maybe different states maybe discovered or with different different fractions from other hospital. That's a very interesting future direction. Thanks.
Hello. Sorry, I didn't quite understand why this problem is framed to be a clustering problem instead of a classification problem, because it seems to me that you have all the label information of the whether or not like there's complication or whether or not it's coming from virus or like the infection source. So why is it not a classification problem?
Why is not a classification?
Yeah, why is it not like a supervised learning problem?
I got you. So although we know so some pneumonia is caused by viral infection or bacterial infection, and for some cases we know that this pneumonia is acquired within hospital or associated with mechanical ventilation. But for most of the cases, the etiology or the pathogen is unknown throughout. Like even the patient have recovered and go back home, the exact pathogen that's causing pneumonia is unknown. So first, the etiology or the heterogeneity of pneumonia is ambiguous, and this may lead to the abuse of antibiotics, for example. And second, even the pathogen is known for different patients, different demographics, their progression trajectory may also differ, and the underlying clinical states may also differ, and that is also not known to us.
Thanks.
Thank you.
We have time for just one more question, maybe. Otherwise, I will. Okay.
I have a question. Are you using all the data up until the person leaves or until they die, I guess, to do this?
So I'm focusing on patients' ICU stay. So I'm only including data from the ICU because first the data is recorded more regularly and more frequently. Patients are constantly monitored within the ICU. And second, this would reveal severe pneumonia, which is of our research interest. So for patients who unfortunately die, usually they just die in ICU. But for patients who fully recover, they would go from ICU to ordinary ward and spend some recovery time there and then discharge to a home or other recovery facilities. And in that case, I extract the extreme survival states as ICU days that's within 10 days of discharge back to home. Does this answer your question?
I guess my question is like, are you using data from like, maybe you could use sort of like cut the data so that it's further away from when they leave or die so that you can use it to have some predictive power? I don't know if that question makes sense. Or
I think you answered about kind of fine-tuning the pre-process. And so we now think that you are not using the data from the entire.
it's not that I'm wondering if I guess because if you're using all the data, it might be easier to tell when it's closer to like when they leave or die. That might be the differentiating step to like sort of differentiate these two. But maybe it might be more useful to sort of separate them out for when they are further away from these sort of two states, if that makes sense.
Yes. So I made or benchmarked or decided choices of pre-processing using only the extreme endpoints. But after that, I conducted the clustering analysis on whole data set. So the states would also including days that's further away from the endpoints.
All right. Thank you, Feihong.
Thank you.
Our third speaker today is Kumar Utkarsh. Kumar is a PhD candidate in engineering sciences and applied mathematics, and he also works with Danny Abrams at the Mathematical Modeling and Complex Systems Lab. His research uses mathematical models to understand pain crisis events, and his modeling approach draws from stochastic processes, dynamical systems, and machine learning. Today, he's going to discuss a self-exciting model for pain caused by sickle cell disease.
Thank you, Andrew. Good afternoon. Today I'll be presenting on a self-exciting model for subjective pain. Now, our data thus far is from sickle cell disease, but we expect to expand the scope in the near future. To start off, what is sickle cell disease? Now, sickle cell disease is a genetic disorder in which the red blood cells deform into these sickle shapes, which restricts the blood flow, as you can see from the figure. And because of the restricted blood flow, pain episodes become the most common symptom. Now, sickle cell disease is a major problem. It affects more than 20 million people across the globe, which includes more than 100,000 people in the US. Now, such pain attacks more than often requires hospital treatment, and more than 50% of patients experience chronic pain. Now, this makes the study of such pain episodes really important, and to be able to come up with a tractable model, which not only explains, but also predicts incoming pain episodes, would greatly improve patients' lives. Now, to form our hypothesis, we look at a certain clinical observation. We learned that 90% of the patients are readmitted within 30 days, which leads us to believe that these pain events give rise to further pain events, making them to be self-exciting processes. Now, can we learn anything by just looking at the time series? The data that we have consists of the timestamps and the corresponding patient-reported pain scores. Now, what if we consider them to be stochastic processes? And more precisely, what if we consider them to be point processes? Now, we do not work with any physiological variables, so we are best off using the likelihood approach. And finally, can we discriminate among different models? Now, since we have no other working models for pain episodes in sickle cell disease, I will be comparing our model with the simple Poissonal model. Now, to introduce the model, it's called Hox process, which is a self-exciting point process. It's a subclass of general non-homogeneous Poisson processes. The conditional intensity function is given by the following equation, where lambda naught t is the baseline intensity, and the self-excitedness comes from the memory kernel function. Ht is nothing but the history of all the pain episode that has happened before the time t. Now, this memory kernel is a monotonically decreasing function. That means the way we set up the equation, recent events have greater influence. Now, for our working Hox process model, we consider the baseline intensity to be a constant, and we introduce two more parameters, alpha and tau. Now, how do we interpret these parameters? Lambda naught, as mentioned, is the baseline intensity. We can consider lambda naught to be the intrinsic homogeneous Poisson process rate. Alpha is the amplitude of impact of prior events. If we look at the equation, if we have the intensity lambda at any point in time, if we observe an event, alpha is the magnitude of the shift of the event rate. Similarly, during the absence of an event, we see a decay, and that decay is characterized by tau, the time scale for impact of prior events. Now, different choices of these parameters can give rise to different long-term behaviors. A simple example can be seen in this figure. Sorry for the small font, but if you focus, lambda naught over here is 2, and if we look at the length of each impact, that's also 2. And over here, if we look closely, we can see some low clustering happening. Now, in this example, I'm using a moderate low tau and moderately low alpha and high tau, giving us low clustering. But what if we flip it and we use high alpha and low tau? We will get a highly clustered event. Now, this is expected, as if we have a high alpha, whenever we get one event, it increases the likelihood of observing more and more events. And if we observe an absence of event, that'll make us the process to decay down even faster, decreasing the rate value and to continue the absence of events. A classic example for such event are earthquakes. Earthquakes are known to be Hox processes for quite long, as they are highly clustered events. Now, we try to get around some of the assumptions in the model I introduced. Our Hox model is given by this equation, which implicitly assumes that the rate at t equals 0 is lambda naught. That implies that we start with the baseline intensity. But this is not always true, because the patient has been in pain all his life or all her life, but we only start collecting the data at a certain point in the person's life. That means that lambda at 0 cannot be lambda naught, because the process has been on for quite a while. To get around that, we introduce a new parameter gamma to represent the intensity at t equals 0. And we modify the equation for the conditional intensity function to be like this. Now, defining the process this way, it implies that lambda at 0 becomes gamma, and we also preserve the decay dynamics of the process. Now, this is a picture of a more realistic way to approach the problem. Now, the solid red line is the t equals 0 of our data set, and the peaks on the left-hand side are the pain events that has happened for the patient in the past, the data that we do not have, and the peaks on the right-hand side corresponds to the data points in our data set. And we start looking at the patient somewhere near the red line. Now, the implementation is a work in progress, because introducing a fourth parameter brings in a few more challenges. One of the challenges is fitting the parameters. So I consider a lot of synthetic data sets, which includes just tail of long time series. And we see that we are able to extract the true parameters. The red line are the true parameters, which are fairly close to the average of the distributions. However, the variance is big enough for making the parameter fitting process to be a challenge. Now, let's backtrack a little bit and talk about the prior challenges pertaining to the data set. Now, we work with patient-reported data. That means that the data sets that we consider are not very high quality. two immediate problems that we can see from these examples is that we have large gaps, and also the data sets are very sparse. Many data points consist of 0 pain scores, which will be eliminated from the analysis anyway, making our lives much more harder. Now, the sparsity brings in a special kind of challenge, because if we think back about the equation, if we set alpha to be equal to 0, we just get a homogeneous Poisson process. That means that homogeneous Poisson processes are subclass of Hawkes processes. So here I have generated a lot of time series with varying number of events in them, and all of them are generated from true Hawkes process. But we see that if we don't have enough data points, the relative likelihood test chooses the Poisson model over the Hawkes model. Because if we don't have a lot of data points, Poisson model and Hawkes model would have similar likelihood, but because relative likelihood uses AIC, which penalizes complexity of the model, it will choose a simpler model. Now, to circumvent that problem in our data set, we try to combine or aggregate patients. Now, how do we do that? We look at temporal distributions of pain episodes for each patient, and we use a two-sample Kolmogorov-Smirnov test, also known as KS test, which takes the maximum distance between two distributions, convert it into the p-value, and conclude whether two samples come from similar distributions or not. In our case, so I'm working with a cohort of 39 patients. The initial model fitting rendered 19 patients to consider Hawkes model over Poisson model. And for the 20 remaining inconclusive patients, if I consider the matrix of p-values for the pairwise KS test, we see that for a certain patient, they have enough patients who share similar temporal distributions of pain. Now, how do we aggregate that? We can simply take the time series arrays for each patient and concatenate them, but that creates a lot more problem, because concatenation implies assuming pain history. Rather, we can just consider different data sets to be different instances of pain data of each patient. Now, this large temporal gap allows the process to reset to equilibrium. That means that naturally we can assume, say, patient 1 and patient 5 have similar distribution. We can assume both of them to be different instances of the same process. The natural way of aggregating the patients and get the model parameters would be to consider the likelihood function of the concatenated series to be the product of individual likelihood functions. Now, some early results. Now, the left-hand side figure shows the histogram of the number of data points per time series. And we see that before augmentation, the number of patients for which we had more than 50 or 60 data points were pretty low. But after augmentation, we see a lot more data sets to have more points. Now, because of that, we are able to do the test with more confidence. And finally, we have 37 out of 39 tests are consistent with Hawkes model. Now, these are early results because I have still not implemented the modified Hawkes model. So these are also slightly wrong results. Now, but this already is promising, right? So as soon as we get over the parameter fitting problem, we are confident that we'll be able to conclude the same. And with that, I would like to thank my advisor, Professor Danny Abrams, and the Dr. Nimish Shah at Duke University Sickle Cell Center for his help with the data set and his clinical inputs. Thank you.
All right. Any questions for Utkarsh?
Very interesting. You are comparing the Hawkes process to homogeneous Poisson process, right? I'm curious why you think that this is a self-exciting process as opposed to a non-homogeneous Poisson process that depends on some other factor in these people's lives, like stress going up and down, causing bursts of pain or something like that.
I think this is fed by clinical observation more like, because the doctor has experienced that whenever a person goes through these pain episodes or pain crisis events, it's more likely that in the near future, they will come back. So Mhm. That's a good point. I mean, that will bring in more candidate models, and for those candidate models to be part of the comparison, we'll have to show some validity of them being better than the Poisson model anyway. So that might be the next step of the process. Like if we can say that this is better than the Poisson model, can we say this is better than some other candidate models? And that would also require a similar study where we show that those candidate models are better than the homogeneous Poisson model. Yeah.
Anybody else? All right.
No, it's really fascinating, and I actually had sort of a similar suggestion that you can transition. You can have a rate for the transition to an activated state or something like that, and there are a multitude of models, and as you said, all models are wrong in a sense. But but there is also the question of that some of them are useful, and in which way do you think kind of understanding these statistics of how things occur could impact treatment, right? Or kind of how to make the patient more aware of risks or of periods that are going to be more intense. Is there a way in which you sort of can use the model to predict kind of periods of higher activity or something like that that could be useful to the patient?
Yes, I think initially we had discussed about integrating this model with more data-informed models that other collaborators have worked with. And definitely, I think using this model and inform it with data-driven models to use more physiological variables, we can have confidence intervals. If the patient is getting a pain episode, then if we make a certain application using these models, the application can give us a confidence interval with certain confidence that, okay, this is the time frame when you can expect the pain to be high. And by getting that sort of confidence or probability, the medication regulation is easier for the doctor. So that way, it can really help the patients.
Good. Yep. That's for the speaker. If not,
well, I have
you have another. Go for it. Yeah.
So one thing that I think may be very interesting in this data and very challenging is an issue of censoring, right? That the patient doesn't report anything below a certain threshold, and it will just appear as a zero. Does your data have any indication that I think it's very plausible that people are censoring, of course. That is like 2, you don't even care, 8, you care. Is there any evidence that people have different thresholds for this censoring? So below something, they never report anything, so their values are always
Many patients have different baseline pain as well. For a lot of patients, they are always experiencing a low threshold of, say, 2. But that 2 can be different for different patients, right? But definitely, a lot of patients always report more than 4. But there are a lot of patients who never report more than 5. But more than often, they're always in pain. So we do see a lot of variability in patient behaviors of reporting.
That's kind of a quick follow-up on Lucia's question. Do you use the intensity of the pain in your model, or just there is or is not a pain?
As of now, we are not. We are only considering all the pain episodes. But as the data gets richer, we will only focus on crisis events or when the patient is above a certain threshold.
Okay, the questions from Professors Braun and Amaral inspired some thoughts of, are there clinically known, like, is the way that sickle cell disease causes these pain events, is that known? And if it is, what's the potential for having biomarkers measured, say, through a blood test that you could observe in these time series, potentially to get at some of these dynamical processes? If you have some underlying indicator of that, you could measure that alongside some of these, see it, perhaps you won't have 0, you'll have some baseline level, and you might be able to detect some of these intermediate changes,
Mm.
get around some of the censoring that Luis was pointing to.
But I think the models I've come across are mostly all data driven. The only other model close to the kind of model I'm doing is more of a mechanistic model. But even in that one, I think medication effects were the focus of the study. And as far as biomarkers go, there are predictive models that uses supervised machine learning models, and then can use PDP plots or certain such plots to find which vital signs are most significant for the predictions. But yeah, that's.
So it sounds like the knowing why the pain episodes occur is not fully fleshed out.
Yes.
Or not well fleshed out biologically.
As per my knowledge.
Right.
You guys already have some degree that
Partially, yes, I have some.
so you have something that's more
Definitely.
because I think that evaluate model
Mhm.
thinking about
Great. Definitely. Thank you.
We are just about at time. If all three of our speakers could come up to the stage or just stand up, and we'll give you another round of Thanks, everyone. We'll see you next week.
Thank you.